Hello, welcome to the video solutions for Unit 5, Lesson 5 on special right triangles. So, it starts by saying use the given triangle to solve the problem, round your answers to the hundredths place. So, it tells us that the measure of angle CBD, so CBD, that's this angle down here, is 51 degrees. It tells us that the measure of CDA is 30 degrees. So let's fill that in. And the measure of CAD is 90. That's already marked for us right here. Doesn't hurt to add the 90 there, but it shows that little square indicating it's 90 degrees. And then lastly, it tells us that CA, the length of CA, is 6. So the first thing it wants us to do is find the measure of BCD. So let's do a different color here. Okay, so angle BCD is this angle right here. So we know that triangles are a total 180 degrees. So if we're looking at this triangle BCD, the whole triangle, we already know that angle B is 51 degrees. So we can take that away, and we know that angle C is 30 degrees. So we can take that away as well. That'll leave us with the remaining angles left in 180, which will be our measure for angle C. So 180 minus 51 is 129. And then we subtract another 30, we get 99. So the measure of angle BCD is 99 degrees. And it is important to make sure we include that degree symbol as well. Question 2, it says find the measure of BCA. So let's change our color up here. So BCA, that's just this part right there. BCA and the measure of ACD. So it wants us to find both sides of that C there. So remember, we know that this angle A is 90. And that's 90 on both sides because it's supplementary. It's a line, so the line has to total 180. So if it's 90 on one side, it's 90 on the other. So let's look at this BCA first. So we know that triangle BCA is 180 degrees. We know we've already used up 90 from that right angle. And we also know that we've used up 51 from angle B there. So if we subtract those, right, 180 minus 90 is 90. So that leaves us 90 minus 51, which gives us 39. So the measure of angle BCA is 39 degrees. Okay, so we're going to follow a super similar procedure for the other side here for this angle ACD. So triangle ACD, well, that's 180 degrees total, and we know it has 90 already because it also has that 90-degree angle in it. We know the angle D is 30 degrees, so we subtract 180 minus 90 is 90, and 90 minus 30 gives us 60 degrees. So measure of angle ACD is 60 degrees. Remember, we know that big angle C, that BCD angle, we said that it was 99. So it's we could also have said, okay, well, if we know BCA is 39 and the whole angle is 99, we can say 99 minus 39. That's another way to get that 60. But that does add up to the angle BCD, which is 99. So perfect. All right, the next thing it wants us to do is find side BC. So we know that, let's get a new color here, blue. We know that CA is 6. So it wants us to find BC. I'll call this H, I guess, for hypotenuse. So there is a few ways we can go about finding this, depending on what type of algebraic work we want to do. I think using trig ratios are the fastest. So let's review those trig ratios, right? So, TOA, right? So find BC. So I'm going to call that H for hypotenuse there. I know all the angles in that triangle, but let's use angle B since it's kind of nice and clearly labeled there. If I want to use, and remember I can use SOHCAHTOA in a right triangle. So right triangle allows this, but only in a right triangle. If it's not a right triangle, we do have other types of trig formulas we can use. So we're in a right triangle. So let's do sine of our angle. Sine of our, and let's use angle B, is equal to opposite, which is 6 over hypotenuse. That's what we're trying to solve for. So we're trying to solve for that hypotenuse. And we know that we have sine of 51 degrees because that's what angle B is. So 6 over hypotenuse. So now let's do some algebraic work to get that hypotenuse by itself. And instead of calling it hypotenuse, let's just start calling it BC because that's what it is. So I'm going to multiply both sides by BC. So BC times sine of 51 equals 6. And then I'm going to divide by sine of 51. So I'm left with BC equals 6 divided by sine of 51 degrees. Make sure here we have to make sure we're in degree mode. That's really, really essential when we're doing these calculations. And then this is just something we can pop right into our calculator. So if we put this in our calculator, 6 over sine of 51, it says round to the hundredths place. So I'm going to put 7.72. The next digit is 0, which means the hundredths place. I just want 2 decimals and the 2. So that 2 does not round up since it's followed by a 0. Okay, let's find BA now. So, let's see, BA. So BA is this segment right here. Again, there's a few ways we can go about this one. Now that we know that this hypotenuse, and I'll write it up on the triangle, that the hypotenuse is 7.72, I can just do Pythagorean's theorem if I wanted to. However, I actually like using trig again. There's no harm in using trig. This time let's use sine of B again. So I'm going to change up my color here. So sine of B, this time I want my adjacent angle to be. So I don't want to use sine. Let's use cosine. But I can use angle B. So cosine is adjacent. So that's the BA side over hypotenuse 6. So I know that my angle there is 51 degrees. And that's going to be BA over, what am I talking about? Over 6. Over 7.72. And actually, you know what? Let's avoid using that 7.72. So my apologies, I'm going to backtrack a little. If I use cosine, I have to use the hypotenuse, which is fine. But the hypotenuse is a rounded number, so let's use exact values as possible. Let's use the 6. So 6 is opposite B. So if I want opposite and adjacent, let's use tan of 51. Tan of 51 is going to give me opposite 6 over adjacent BA. And if I don't want that BA down the bottom, I actually could use angle 39 instead. But I'll use 51 and I'll do some algebraic work, right? I'm going to multiply both sides by BA. So I get BA equals tan of 51. BA times tan of 51 equals 6. And then divide by tan of 51. So BA equals 6 over tangent of 51 degrees. Again, that mode is really important. We should still be in degree mode. Okay, so if we type that into our calculator, we get about 4.8. Now the next two digits are 4.858. So 58, that 5 is going to round up. So I'm going to make it 4.86. We're going to round upward since we want to round to the hundredths place. And I can fill that in on my table here, 4.86. Okay, find CD. So CD is the hypotenuse in our other triangle. Let's There we go. There's a color I haven't used. So we're looking for this hypotenuse here. Now, this is a special right triangle, so we could do this one without using trig if we wanted to, but we'll use trig since we already started that path. So to find CD, well, that's the hypotenuse, so let's do sine of 30 degrees equals opposite 6 over my hypotenuse, which is what we're looking for. So I'm going to multiply both sides. Instead of writing hypotenuse, I'll write CD. So let's multiply both sides by CD. So CD times sine of 30 equals 6. And then I'm going to divide both sides by sine of 30. So 6 over sine of 30. That gives us 6 divided by 1/2. So I don't need to round this one because it comes out to a nice exact value when I put it in my calculator. Or again, if you know sine of 30 off the top of your head, because it is a special right triangle. If you don't know it yet, that's one we're going to get real familiar with as we continue working with these angles. But it's 6 over 1/2 or 12. So CD is 12. There we go. Okay. So I'm going to fill that in. CD is 12. Okay. And then find AD. So AD right there. So again, let's use trig. 12 came out to a nice number, so I could use cosine or tangent. Let's do cosine this time. Although sometimes it's good to avoid using values you found, just in case you made a mistake. But I'm confident we got 12 is the correct answer. So let's do cosine of 30 is AD over hypotenuse 12. Okay, so I'm going to multiply by 12 to get AD by itself. So 12 cosine of 30. And again, you actually could use exact values for this, but it does tell us we can round to the hundredth place, so I will do that one. So we'll put this into our calculator. Which gives us 10.392. So the 9 does not round up because it's followed by a 2. So 10.39. And one thing I just noticed I've been leaving off of all of these, we were specifically told that CA is 6 feet. So I actually can go ahead and add units to all of these. So I'm going to do that because we definitely want to include units when we have them. So this is 12 feet. And 4.86 feet. Let's put BA equals, just to be really clear. It's an approximate value. There we go. And lastly, this 7.72 feet. So BC equals 7.72 feet. So just get a little more exact answers. All right, question 7 wants us to find BD. So we could use this big triangle, but we already know that we have BA and we have AD. So we can go ahead and add those two things together, right? BA from question 4 was 4.86 feet, and AD from question 6 was 10.39 feet. So if we go ahead and add those together, we're going to get our length for BD. So let's think for a second. Okay, we got 10 plus 4 is 14, but that 0.86 and 0.39, those add to 1.25. So BD then is 15.25 feet. Okay, question 8. It wants us to find the area of BCD. So notice BCD is the big triangle, which is great because we need the height to find area. So area of a triangle is half times base times height. Now, the height and base change based on the orientation, but let's use 6 as the height since we have that. Since 6, if we're going to use 6 as our height, that's CA, that means BD has to be our base. So if we use 6 as our height, that means this is actually BD. So base, I'll write out the words, base times height. So if we're going to use 6, that makes BD our height. And we just said that we know BD, right? We just said that BD is 15.25 feet, and we know that it is a height of 6. Now, notice I have feet twice, so my area is going to be feet squared. So I just have to multiply these. So 1/2 times 6, that's nice and quick to do. That gives us 3. So 1/2 times 6 is 3. And then we multiply 3 by 15.25. That gives us 0.75. So the area is 45.75 feet squared. There we have it. Okay, let's move on to question 9. So this one says, fill in all the missing measures in the triangle. So this one, it tells us we have this 90-degree angle right here, and we know that this is isosceles, right? This is isosceles. It's showing us that the two sides are the same, which means the lengths are both 6 inches. So we have that. And there's 180 total. We've already used 90. So that means each one of these angles must be 45 degrees. If their sides are equal, so are their angles. So we have the angles. Now we just need to find that last side. Let's use Pythagorean's theorem. And if you know the ratios for a 45, 45, 90, absolutely go ahead and use that. Right now we're just going to act like we don't know this. So my hypotenuse there, I'll do h for hypotenuse. So h squared. So we get 36 plus 36 equals h squared. Well, it gives us 72 equals h squared. So if I take the square root of both sides to get that h alone, I'm not going to do plus or minus since we're dealing with side length, so we want everything positive. Well, this is 2 times 36, so the square root of 36 can come out, and I'm left with 6 root 2 as my last value there. So 6 root 2. Okay, let's go on down. This one we know, we have a 90-degree angle here, and tells us that top angle is 30, which means there must be 60 left, right? So for this one, again, we can try to use our special right triangles, or we can try to use trig if we want, but we're going to go to the special right triangle that we saw. Sort of, if we scroll up to our triangle right here, this was also a 30, 60, 90, right? We said this was 60 degrees right here. I never filled it in. And notice that the 30-degree angle, when that was 6, the hypotenuse was 12. It was double. So we're actually going to do that same ratio, that if this hypotenuse is 8, across from 30 is going to be half of that. So this is going to be 4 feet. If we want to double check that with trig, we certainly can. So we could do, let's do sine of 30 equals opposite. So I'll just call it opposite over 8. So if I want that opposite by itself, I do 8 times sine of 30 degrees equals my opposite side, which gives me 8 times 1/2, or 4. So algebraically, that's how we found that 4 feet. Now, since we have two sides, let's do Pythagorean theorem to solve the last one. I'm just going to put a y as a placeholder there. So y squared plus 4 squared equals 8 squared. So now 4 squared is 16. 8 squared, we get 64. So we're going to subtract that 16 from both sides to get the y squared all by itself. So y squared equals, well, 64 minus 16 gives us 48. So we take the square root of both sides. Now, 48 does have some, remember, the good way to go about this is trying to see if we can divide these numbers by a perfect square. And this one does, 48 is multiple of 16 times 3, and since 16 is a perfect square, we can take the square root of 16, which is 4, and the 3 is left on the inside. So this is going to be, I'll keep the y there, 4 root 3 feet. Okay. Let's go down to the next one. So I see a 60. Remember, this is 90 right here, which means we have another 30-degree angle here. So very similar to the one above it. This time across from 30 is 13. So let's do sine of 30, I guess. Again, equals opposite. Well, opposite is 13 over hypotenuse, right? That's what we're solving for right there. So sine of 30 is, well, let's multiply by the hypotenuse first, and then divide by sine of 30. So since we've done this a few times, I'm going to kind of do it in one step. You can think of it as cross multiplying if you want, but that ends up giving us 13 over 1/2, which is 26. So we end up with 26. So notice again that hypotenuse is double the side that's across from the 60-degree angle. And I could have started with the other side, but I knew this one would come out a little bit nicer. So let's use Pythagorean theorem now to find this other side. I'll give it a placeholder of x. So x squared plus 13 squared equals 26 squared. And again, if you've already started to pick up on the ratio, you can go ahead and use that. Right now, let's do 26 squared is 676, and 13 squared is 169, right? Yeah, it is. Okay, 169. So then we do 676 minus 169, right? We want to move that over to the other side, which gives us x squared equals 507. Now that's a number we might not recognize off the top of our head, but notice that 5 and 7 add together to be 12, so it's definitely divisible by 3. So let's do 3 times. Well, it's 3 times 169, and we just found out that the square root of 169 is 13 because we just did 13 squared to get the 169. So this gives us 13 with the root 3 left over. So 13, and this is centimeters. Let me add centimeters there. I'm going to need a little more space. So 13 root 3 centimeters. So there's question 11. Question 12. Again, we see a 60-degree angle. So 90, that means this one must be 30. And hopefully we're starting to pick up on a pattern here. So let's look. We've talked about one of the patterns a little bit already. I haven't really mentioned the other one, where our hypotenuse is always double the side length that's across from 30-degree angle, right? We see it there with 8 and 4. We also see it with 26 and 13. So our hypotenuse is double that 30-degree angle. But let's look at the relationship between the 30-degree angle, the side across from 30, and the side across from 60. Notice when our side across from 30 was 4, our side across from 60 was 4 root 3. So it's the same side times root 3. We're seeing the same thing here. When it's 13, we got 13 root 3 across from 60. So this is not a coincidence. This ratio will hold true whenever we have this 30, 60, 90 triangle. So let's use that for this one. Let's start, we know the hypotenuse. So let's start across from 30 is going to be half. We're going to get, 11 centimeters. And then across from 60, we're going to take that 11 and multiply it by square root 3. And you can use Pythagorean theorem to check all those But that's it. Once we're able to identify the ratio, this problem becomes much faster. Okay, here we go. We have 90 degrees for question 13, which means this angle is 45, and this angle is also 45. Well, since this is isosceles, this must be the same 1 centimeter. And notice, let's look at the pattern we saw for the 45, 45, 90 at the start. Notice it was 6, 6, and then 6 root 2. So the hypotenuse was root 2 times what the other side length was. So let's see if that holds true here. We'll do Pythagorean theorem because it's only our second one of these. So equals our hypotenuse squared. So 1 squared plus 1 squared is just 1 plus 1, or 2. And then to get that value by itself, we have to square root both sides. I can't simplify the square root of 2 anymore, so that's just our final answer. It's square root 2 centimeters. So the same ratio is held true, right? If I want to put a 1 in front of it to really emphasize it's 1 times square root 2, I can certainly do that, where the hypotenuse is the side length times square root 2. So here we have 12 centimeters as our hypotenuse, and we see this is 90, which means we have a 45-degree angle and a 45-degree angle since this is isosceles. So let's say you don't trust your pattern yet. That's okay. We know that these are the same. So I could still use Pythagorean theorem. I could say x squared plus x squared, because I know those are the same, equals 12 squared. Well, that gives me 2x squared equals 144. So let's divide by the 2 to get rid of it. So divide by 2. That leaves me with x squared equals 72. So now I'm going to take the square root. So square root of both sides. And remember, 72 I can write as 36 times 2. And the square root of 36 is 6. So 6 root 2 is what I get for that x is. So 6 root 2 centimeters. Now, this one's not quite as obvious to see the pattern, but let's just kind of do this off to the side and think, does this pattern hold true? Is 6 root 2 times 2, is that 12? Well, root 2 times root 2 is 2, so we do actually get 12. That pattern holds true. I could have divided 12. Another way to get this was to get those side lengths is I could have divided 12 by root 2, and then I could have rationalized. So I'm going to put or. So that becomes 12 root 2 over 2, which is 6 root 2. So 2 different ways of getting that answer. Okay, let's go down to problem 15. There we go. There's some directions. So use an appropriate triangle for problems 9 through 14 to find the exact values of the trig ratios without using our calculator. So we found 2 patterns from those triangles. Let me do my best to sort of draw these as accurately as possible. It's not quite connected, but that's okay. So let's call this one our 30, 60, 90. So let's say that this is 60 degrees and 30. So I'll use 2 for the hypotenuse, I suppose. We're going to use 1 a lot there, but right now I'll use 2. So if our hypotenuse is 2, that means the side across from 30 is half of that, which is 1. And the side across from 60 is 1 times root 3. So those ratios will always be true. Each of the triangles will reduce to those 2 things. Again, I could use a 1, and then I divide everything. So let's actually do that. Let's show the other version of that. So I'm going to copy what we did there. And these are not to scale. Right. So instead of using a square root 3 or 2, what if I divided everything by 2 here, right? Divide by 2, divide by 2, divide by 2. Well, this 2 over 2 is 1, and this just stays 1/2. And square root 3, over 2. So those are just two different ways to see that same triangle. All right, let's do the 45, 45, 91. Oh, there we go. Make that a little taller. So, not my best work here. I'll just hand draw this in so for time. All right, so if this is the same, this is the same. We have a 45, 45 degrees, and 90. So for this one, we saw it was 1, 1, and then 1 root 2. And once again, I can actually, if I want to divide everything by root 2, if I don't want that to be, if I want that hypotenuse to be a 1, and zoom in here. I didn't give myself too much space. If I divide this by root 2, that becomes a 1. So if I want to think of dividing everything by root 2, I'm going to have other side lengths. However, 1 over root 2, that's not a proper way to write our answer because we have a radical in the bottom. So I can write that as root 2 over 2. So that's what those side lengths become if I divide everything by square root 2. Square root 2 over 2. There we go. Okay, so we have our triangles there. So sine of 45 degrees. Well, what's nice about sine and cosine of 45 degrees, when it's 45 degrees, opposite, these are actually going to be, I meant to keep that in my purple color because we're doing 45. These are going to be the same. Opposite 45 is 1, and hypotenuse is square root 2, or we can use this triangle right here, right? Square root 2 over 2 divided by 1, because that's our hypotenuse, which is just square root 2 over 2. Tangent is, I can use either triangle. I'll use my square root 2 over 2 triangle. But if it's opposite over adjacent, so I have to divide those two sides by each other, but since they're the same, that's just going to come out to a 1. Okay, so let's look at sine of 30, cosine of 30, and tangent of 30. So we're using this 30-degree triangle. So our 30-degree angle is right here. So sine opposite 30 is 1/2 over 1, or just 1/2. Adjacent to 30, we see that square root 3 over 2 divided by hypotenuse 1, or just square root 3 over 2. And tangent, let's use this triangle instead for tangent. That way we're not dealing with fractions and fractions. So tan opposite 1 over square root 3, but remember we don't want to leave radicals in the bottom, so let's rationalize by multiplying by square root 3 over square root 3, which gives us square root 3 over 3. So that's our tan of 30. Okay, so now sine of 60, cosine of 60, and tangent of 60. I'm actually just going to highlight to really emphasize where that 30 was, and really emphasize where this 60 is. Right, our 60 is down here. So for these ones, we're looking at that 60-degree angle. So opposite 60, right, opposite 60 is square root 3 over 2. Hypotenuse is 1, but when we divide by 1, it doesn't change anything. Cosine of 60, well, adjacent to 60, we have 1/2, or 1/2 over 1, which doesn't change anything. And then tan of 60, again, I'll use our smaller triangle. Opposite of 60 is square root 3, and adjacent is 1. So really, that's just square root 3. Okay, there is our 60-degree angle trig ratios. So let's move on to our Go problems. So Go says, identify the type of function, linear, quadratic, or exponential, represented by the table or graph, and write the explicit equation for the function. So let's look at 18. Let's see if we can find a pattern. Let's check for linear first. Right here, our difference is we're adding 3. Right here, we're adding 6. So not linear. we can see that. Here we're adding 12, and then 24, and then 48. So it's definitely not linear because we're not adding a constant number each time. So let's look to see if the second difference is constant, right? Here we added 3, and here we added 6, so we're not constant in our second difference. So let's check for exponential, right? Remember, exponential is we're looking for a common ratio or multiple. So notice our x values, they all increase by 1. So that's actually important to note, that that's a constant increase, that they're all going up by 1. So the pattern we see here is we're actually multiplying by 2. It's doubling every single time. So this right here is our initial value. And when we see this pattern of doubling every time, this is going to be, did they give us a spot to put our, yeah, they did, type of function. This is going to be an exponential function. So it's exponential since it's doubling every time. Our initial value, remember, exponentials are in this form, y equals ab to the x. Well, our a value is 3 because that's our initial value, so 3. So when we're talking about the equation, we're going to say y equals 3. Now our growth factor, that b, so growth factor. Since our x's are only going up by 1, we can see our growth factor is 2 from the table. It's doubling every single time. So there we have it, y equals 3 times 2 to the x. Okay, question 19. So again, let's check for linear first. Are we going up or down by a constant number? So 8 to 2, that's a decrease of 6. And then a decrease of 2, so it's definitely not linear because we don't see that 6 again. So let's check for exponential first this time. Right, this would have to be times 1/4 to get 8 to 2. And this one is not, if we check for times 1/4, that doesn't work. So it's not exponential, right? So it's not linear. It's not exponential. So let's check to see it's our quadratic. And again, I should always point out our x's are increasing by 1. So exponential, let's see, this first difference is, like we said, we're decreasing by 6. Here we're decreasing by 2. Here we're now increasing by 2. And we're increasing by 6. And we're increasing by 10. So the difference between these two numbers, right, we see that that's a 4. So we increased 4. Here we increased 4 again, increased 4, increased 4. So the second difference in constant, that makes this a quadratic. So a quadratic function. Okay, so now let's write our quadratic equation. Okay, so there are a few ways that we can get the quadratic equation, but what I really like about the patterns that they gave us here, notice for instance, I'll highlight a couple, 0, 8, and 4, 8. Since those have the same output, that means those points are symmetric. Same thing with 1, 2, and 3, 2. So those ones have the same output, the same y value. That means they're symmetric. So the axis of symmetry, the axis of symmetry has to be directly in between those x values. Well, the point in between 1 and 3 is 2, or the point you can think of, the point in between 0 and 4, that's also 2. That makes this point right here our vertex. So our vertex is 2, 0, because it is that midpoint of where all the symmetry is. So we have our vertex. So y equals a x minus 2 squared plus 8. So we have hk. I can put a plus 0 in the end. So to find that a, I could do a few things. I could actually look at the pattern, or since I have everything else, I could plug in any point. Let's plug in 0, 8, right? Let's plug 8 times 0 minus 2 squared. Well, that gives us a times negative 2 squared, or a times 4. If I divide by by 4 on both sides, I get a equals 2. So that's one way to get it. You can certainly use other methods for getting the vertex, but that means our initial value, sorry, not our initial value, our leading coefficient is 2, and then x minus 2 squared is the rest of that equation. Okay, let's go to problem 20. So, problem 20, this is a parabola, right? So we have a parabola. So we have a quadratic. And normally we would want to test to make sure this is a quadratic and not something of, let's say, degree 4 that looks very similar to a quadratic. But the directions did tell us we're looking for linear, quadratic, or exponential. So we can trust that this one is quadratic. So let's look at the equation. Well, the vertex kind of stands out to us there. We see that we're counting by 1 since we see that -5 and +5. So our vertex over 1, 2, 3. So our axis of symmetry is at -3. So that's the x value of our vertex. And we're down 1, 2, 3. So -3, -3 is our vertex. So since we have the graph, let's just count that rate of change when we go over 1, up 1, 2. So over 1, up 2 means our leading coefficient must be 2. You could find this algebraically as well by plugging in a point. Maybe you see that you have the point -2, 0, and you go ahead and you plug that in. But I'll use our 2 that we got from just visually looking at our graph. Remember, we changed the sign of x, so x plus 3 squared. We don't change the sign of the y value of the vertex. So there's our equation for question 20. Okay, let's go down to 21. So this time we have an exponential. And this is exponential decay since our function is decreasing. So we can see here's our y-axis, right? So we can see that it crosses that y-axis at 0, 8. So we're thinking about y equals ab to the x. We can see that initial value is 8. So I'll write exponential here. So at y equals 8, now we need to find our b value, our growth factor. So here I can see this point looks pretty clear right there, 1, 4. So we went over 1 and we went down by half. So that means my decay, since that only went over 1, must be 1/2 x. Again, you could actually plug that in if you feel a little bit more comfortable. Now we know that the 8 is, you could plug in 4 for y and 1 for x. We divide both sides by 8. We get 1/2 equals b to the first, which is just b. So that's one way we can find it algebraically. Okay, and that's it for this Ready, Set, Go. Hopefully you found this video helpful. Thank you for watching.